Is it working? Okay, it starts. So, hello everyone. Welcome to the SPAAM seminar this week. And our speaker today will be Lorenzo Quarisa, who is a PhD in mathematics. And he will be talking about the vanishing viscosity limit for the Navier-Stokes equations. So, Lorenzo, please.
Okay, thank you. All right, so we're talking about the vanishing viscosity limit for the Navier-Stokes equation. So a central problem in mathematical fluid dynamics is understanding the behavior of fluids as the viscosity becomes really small. So a viscous fluid will satisfy a certain set of equations, which is called the Navier-Stokes equations. Okay, so I'll start by writing down these equations. So let's abbreviate with NS. So we have a fluid will be represented by a vector field U. So U will be a vector field in, say, RD for some dimension D. I mean, typically D will be equal to 2 or 3, but for now we stay in a more general case. All right, so we have the time derivative of U plus U dot the divergence of U. So this is basically the convective term, and all right, so this can be written as like this. Okay, so we don't have any doubt about what this means. Okay, so plus the gradient of the pressure. So this will be a scalar field. I mean a scalar field, and this will be equal to the viscosity times the Laplacian of U. Then we also have the divergence precondition. So this will correspond to the fact that U is an incompressible fluid. And then we have some set of boundary conditions. All right, so these two equations are satisfied on a domain omega contained in RD. And the boundary condition, of course, will be satisfied at the boundary. Okay, so these are the Navier-Stokes equations. And the boundary condition, I will specify it later. Now, if we imagine that the fluid has no viscosity, so here nu, the viscosity is represented by this parameter nu, which is strictly positive. So if we imagine that there is no viscosity, then basically this term disappears, and we get the Euler equations, abbreviated with E. So it's basically the same equations, except there is no term in the right-hand side. So this is equal to 0. We still have the divergence precondition, and the boundary condition here, I will write it immediately, and it's the fact that U dot the normal versor equals 0 at the boundary. So this means that the fluid is tangent to the boundary, and it means that the fluid cannot go in and out of the boundary. So this is a very intuitive boundary condition. You don't expect the fluid to be able to pass through the boundary normally. All right, so let's go back to the boundary conditions for Navier-Stokes. So here we have, we can consider two types of boundary condition. One is the so-called no-slip condition, which says that U equals 0 at the boundary. So this is, of course, different from the boundary condition on Euler, because we don't require just the normal component to be 0, but the entire vector field should be 0. So this means that basically the fluid does not move at the boundary. And this makes sense because it's a viscous fluid, so we can expect that at the boundary, the viscosity will make the particles stay still, basically. But there are, of course, there's also another type of boundary condition of interest, which allows some slip at the boundary, and it's called the Navier condition. And it says that the rate of strain at the boundary is proportional to the tangential velocity. So, all right, so we have the symmetric gradient computed at the normal vector, and then we take the tangential component. and we say this is equal to some negative, so alpha is strictly positive, times the tangential velocity. And we couple this with the other condition that the normal velocity is 0. So both of these are, of course, stronger conditions compared to the boundary condition on Euler. And this will be important in what follows. All right, so now that we have described the setting, I will write down the main problem that we will consider today. So we have this question. All right, suppose that the initial conditions. All right, so okay, so let's call U nu the solution to Navier-Stokes. So it will depend on the viscosity, and UE the solution of Euler. All right, so there we go. So suppose that initially the difference between the two, so time t equals 0, and here we take L2 norm on omega, and this goes to 0 as the viscosity goes to 0. And then we ask ourselves whether or not this carries over to a positive time t. So suppose also that both U nu and UE are defined on a common time interval 0 capital T. And then we ask ourselves if this convergence solves in the entire time interval. So this is the main question, and yes, so we're trying to understand whether this holds or not. I mean, this intuitively could make sense because the Euler equation is obtained by plugging nu equals 0 in the Navier-Stokes equations. But of course, there's the problem that the boundary conditions are different. So this is the main problem, which could make this statement become false. So what I will try to do now is try to give you an idea why this problem is difficult to solve. And then I will show you, I will say the most important classical result, which is a partial result in this problem. So, all right, so if one wanted to prove that this statement is true, the simplest approach will be to try to estimate this quantity by using energy estimates, because here the question is formulated in terms of the L2 norm. By the way, if I ask this question with a norm, a stronger norm, such that, for instance, this norm implied pointwise convergence at the boundary, like for instance, I could have like an HS norm for S large enough such that we have a trace at the boundary, then this will be trivially false because of the difference in the boundary conditions. So if U nu is 0 at the boundary, but UE is not, then this will make the statement fail immediately. But here we just have the L2 norm, so of course it doesn't imply convergence pointwise at the boundary. So this could still be true. So if we write down the equation, so let's define W as U nu minus UE. And if we subtract the two equations, then we can find out the equation solved by W. So we have something like this. So here, okay, so I'm not going to worry about the pressure, so I will just write the gradient of P. And here we have the viscosity times the Laplacian of U nu. Of course, there is no Laplacian in the equation for UE, so we just have U nu. So if we want to derive an energy estimate, we would multiply both sides by W and then integrate over the domain. And if we do this, then, okay, so let's see what we find out. So, all right, so the first term, we will get the time derivative of the L2 norm. By the way, here I'm assuming that the solutions of the two problems are smooth. So I'm talking about strong solutions here. And yeah, so these, the smooth solutions always exist locally. So if omega is RD, then the solutions, the Navier-Stokes, can be defined on a common time interval. So that makes sense. Whereas if omega is a general domain, then we don't know that strong solution exists on a time interval independent of the viscosity. So in that case, one would have to consider weak solutions. But for now, I will assume that the solutions are smooth, although this probably works also for weak solutions. So, okay, so if we do this, then, all right, so let's see what we obtain. So I will write derivatives using indexes, and I will assume summation over I and j. So we have this. All right, so the gradient of the pressure dot W, and then here we have this. All right, so what happens here is that we can integrate by parts many of these terms, and thanks to the divergence precondition, which is satisfied by W. So of course, W will also satisfy the divergence precondition. We'll have many simplifications. So for instance, this term will disappear because if we integrate by parts and using the divergence precondition on W, this will be equal to 0. And also, of course, we know that W dot n equals 0, which follows because both U nu and UE satisfy this condition. So this term disappears. This term will also disappear. Because this is equal to 1/2 dy absolute value of W squared, and then we can integrate by parts and use the divergence precondition, so this one will also disappear. This one we can't do much, but we can bound it by the gradient of U in the L infinity norm times the L2 norm of W squared. So far so good, but the main issue is this problem, this term here. So in this term, we can't just integrate by parts because, all right, so if one tries to integrate by parts, so we get this. But the problem is that when you try to use the divergence precondition, the derivatives are hitting the. So instead of having W dot n at the boundary, you have derivatives of W dot n. So you can't simplify those. There's a boundary term that doesn't disappear. So that's an issue. So, all right. So let me think about this for a second. All right, so if we write down this equals this. All right, so this one works because the boundary term will be this. Yeah, so, okay, so that's the main issue, right? So this term here does not disappear because we have that the normal vector is multiplied by dy uj nu, and this does not vanish because we already know that u nu vanishes at the boundary, but we don't know that the derivatives vanish at the boundary. So this is the main problematic term, which means that we can't prove this immediately by using energy estimates because everything else will work fine, right? Like here we have this. So this is a negative term, so we can bring it to the left-hand side. And the other term is this. And this is also fine because we can use Young's inequality and we can split it into a sum of two quadratic terms, one with the viscosity, which can be absorbed by the term on the left-hand side, and the other just depends on UE. So the main problem is this term circled in red here. This one we cannot say that it is non-positive. So we cannot proceed using energy estimates here. Yeah. So of course, Wj is not equal to 0 because we have this disparity of boundary conditions. So this is the main problem. Okay, so that shows why you can't immediately prove this using energy estimates. Now, of course, if omega was the entire space, then we will, as long as we assume that there is sufficient decay at infinity, then we don't have to worry about this term at the boundary. So this term vanishes, and you can complete the energy estimate and use Gromwell's lemma to deduce that you do have convergence for all time. So if the domain does not have a boundary, so if the domain is the entire space, then you do have convergence, and the answer to the problem is positive. Now, okay, so now I will show you, I would say, the most important result that has been proven so far for the non-slip case. And this is called the Catalyst Criterion, and it's from the 80s. So, okay, so what this criterion says is that it doesn't provide an answer to the question, but it provides an equivalence with another statement. So it says that, all right, so we are still in the same assumptions that we were considering previously. So convergence of the initial conditions at time 0. So what it says is that you have this convergence in L infinity 0 to L2, if and only if this quantity, so we have the viscosity times the integral from 0 to t of the gradient of u nu in the L2 norm squared goes to 0 as the viscosity goes to 0. And this L2 norm is taken not in the entire domain, and this is the main point of interest, but in this strip gamma c nu. So this will be a strip around the boundary of size c nu. All right, so this is gamma c nu. So, okay, so what it is saying is that for this type of convergence not to hold, there would have to be the gradient of the solution of Navier-Stokes would have to become really large in a strip around the boundary of size c dot nu. So it's asymptotically equal to the viscosity. So this is a really small strip as the viscosity goes to 0. And it is interesting also because typically what is observed is that the difference in behavior between low viscosity fluid and an inviscid fluid happens in a boundary layer of size square root of the viscosity. So this is much smaller than the boundary layer which is typically observed. And yeah, so the implication from the left to the right side is fairly easy because, of course, like by the energy estimates, similar to what I was showing earlier, we know that U nu at time t equals this term here. So here we take the L2 norm in the entire domain. And sorry, this should be at time 0. Whereas for the Euler solution, we don't have any energy dissipation. So the energy is simply constant over time. So if we take the limit as the viscosity, so if we assume that convergence does hold, then of course we also have convergence of the L2 norms. And so it follows that this term must go to 0. And of course, this term is larger than if we take the L2 norm just on a strip around the boundary. So the implication from the left to right side is basically trivial. But the implication from the right-hand side to the left-hand side is what makes it really interesting. So to solve this problem, Cato introduces a boundary layer. So you have to introduce a function v such that the divergence of v is 0 on omega, and v equals ue at the boundary, and the support of v is contained in the strip of thickness c nu. And if you introduce something like this and you consider the Euler solution, then if you take ue minus v, then this equals 0 at the boundary. So this is the main idea, and then you can test the Navier-Stokes equation. So if you estimate u nu minus ue, all right, this will be equal to something that goes to 0 as the viscosity goes to 0, plus 2 times the initial condition of Euler. This essentially by the energy estimates that I've written above. And then plus, minus 2 u nu inner product with u nu minus v. Ue minus v. All right, because this is equal to, sorry, there's a missing, I should have this one step here. So this plus this minus 2 u nu ue. So this is asymptotically equal to this as nu goes to 0 because the support of nu is contained in this strip of size nu. So if you take the L2 norm, it will scale as positive power of viscosity. And then using the weak formulation of the Navier-Stokes equation, we find out that this can be bound basically by a constant times u nu minus ue, all of this, plus some term which is bound by a constant time the quantity described above. So nu integral from 0 to t of gradient of u nu L2 norm squared. And because this goes to 0, then we can apply Gromwell's lemma and conclude the proof. So this is the main idea. And yeah, so this shows that what is really important is what happens in a, so for this type of question, what is really important is what happens in a strip of size asymptotically equal to the viscosity. All right, so this took longer than expected. Yeah, so this shows that the boundary condition in the Navier-Stokes equation, which is different from the boundary condition in the Euler equation, means that it's really difficult to give an answer to this type of question. So I guess my time has run out. I want to talk about boundary layer theory, but there isn't really time, so I guess I'll finish here. But of course, if you have any question, I'd be happy to answer them.
So thank you very much. And let's unmute ourselves and applaud for Lorenzo's talk, please. I will stop recording.